Hello, Mr. Miller here, online math teacher. Welcome to my channel. Today we're going to be continuing my video series on hypothesis testing. So if you find this video helpful, consider smashing the like button, subscribing, and let's go. So, in particular, I want to talk about what is a hypothesis test today. So, hypothesis test, it's a type of significance test. So it's some sort of structured procedure so you can compare observed data to some sort of claim. So there's multiple kinds. This is just one type of significance test. Your hypothesis test is going to start out needing a hypothesis. If you want a hypothesis, it's an educated guess or claim about something. So maybe it's about medicine, maybe it's on some observation in society, maybe it's on survey data, just some sort of educated guess or claim based on that. And the main thing is it needs to be testable. You need to be able to survey, sample, experiment, or simulate. I didn't add that here to be able to help gather data to evaluate your claim. So your hypothesis test itself is going to consist of two hypotheses. So those hypotheses are your null hypothesis and your alternative hypothesis. And these hypotheses are made before you collect data formally. So you set up a hypothesis test, then you collect data later on. So your null hypothesis, this is what's traditionally accepted. It's what you want, what people claim typically, but you want to find evidence against this. So maybe it is the mean test score is 75%. So your null hypothesis will have a form of the parameter of interest and what's the value it's equal to. It's the claim you seek evidence against. It's not what you want to show. The alternative hypothesis, that's your parameter is greater than, less than a value, or not equal to a value. And this is the claim that you hope or expect to be true. It's what you want to find evidence to support. So alternative hypothesis, this is what you want to find evidence to support. Null hypothesis is what you want to find evidence against. So here's our first example. A friend claims they are a 70% free throw shooter. You are skeptical because at last practice, your friend took 50 free throws and only made 25 of them. So the proportion of shots he made was only 0.5. He made 50% of them. That's pretty bad if he's a 70% free throw shooter. Typically, you want this to be random. We're going to skip over that for now. So what I could make as my hypothesis test is they're claiming they're a 70% free throw shooter. So the proportion of shots they think they'll make is 0.7. Well, we think it's less than that. So our alternative hypothesis is going to be that true proportion of free throws your friend would make is less than 0.7, because that's what you want to find evidence to support. So you notice I stated my null hypothesis, my alternative, as well as what that parameter is that I'm interested in studying. And this is called a one-sided alternative hypothesis because that P is less than 0.7, or if it was greater than something. If it's not equal to, that's called a two-sided. A two-sided example could be something like this. You read an article that claims high school students get an average of 2.5 more hours of sleep on a non-school night versus a school night, and you're not sure if this holds at your school. So the claim, your two hypotheses are, it's either true, it's going to hold at your school. So this true mean difference of sleep is 2.5 hours, or it's not 2.5 hours. And that's what you think. You don't think it holds at your school. So you're going to make your alternative hypothesis mu is not equal to 2.5, whereas your null hypothesis is mu is equal to 2.5. So, and mu is just that mean difference in hours of sleep. So this is an example of a two-sided alternative hypothesis because that we have this not equal to symbol in our alternative hypothesis. So these are two different examples. Now going down this same road, we also need to collect data, like I said. So you've now stated your hypothesis test that you want to use. Well, we now need to collect our data. So you might survey, sample, experiment, simulate, something like that. For our basketball example, it's going to make more sense to simulate. And you can simulate it using a computer, names and act, cards, dice, whatever really helps, whatever floats your boat in the moment. So you could do that there. In our mean difference example, you're not really going to be able to simulate with a computer like you could for the basketball example. So you're probably going to want to conduct a survey within your high school asking students how many hours of sleep they got on a random non-school night versus on a random school night, and then you'll calculate your mean difference. This Because that you're surveying, just make sure you follow good survey protocols. Simple random sample, stratified random sampling, cluster sampling if done well, because it's kind of convenience sampling in a sense. Whatever is going to make your life best, though. Well, once you've collected your data, you need to analyze it. So, our goal is to find evidence against that null hypothesis. Does our evidence support that? So, what's really what we're going to ask, what's the likelihood of obtaining the results we had in our data if we assume the null hypothesis is true? That's really what we're looking at. So, and that's what ties back to our p-value. With that assumption your null hypothesis is true, the p-value is defined as what's the probability our sample statistic takes on a value as or more extreme than what we observe from our collected data. If it's a very low probability, that's going to indicate strong evidence against the null hypothesis. If it's a very large p-value, that's going to be very minimal evidence to no evidence against the null hypothesis. So say we're back in our basketball example. So I run 500 simulations of a 70% free throw shooter taking 50 free throws, and then I record the proportion of those trials where 50% or fewer of the shots were made. Well, only one of those 500 shots ended up or trials had less than 50% of the free throws made. So that meant my p-value is 0.002. And since that's very small, the probability of a 70% free throw shooter making 50% of their shots or fewer, then that's substantial evidence against the null hypothesis. So we reject your null hypothesis and accept the alternative hypothesis that says your friend is a sub 70% free throw shooter. So they're overestimating their abilities here. In our school problem, if I've conducted a survey and in my survey reported back that the mean difference was 1.5 hours with a standard deviation of 0.5, I ask what's the likelihood of getting a difference between 2.5 and 1.5 or 2.5 and 3.5 or more extreme. So it's a 1 hour difference here. What's the likelihood of getting a sample that was 1 hour or more different than this claim? And that p-value ends up being virtually 0%. So since the odds of us getting that value were so small, they were effectively 0, you have substantial evidence against the null hypothesis. The likelihood we get something that extreme or more extreme when we collect our sample data, we're not likely. So again, you would reject your null hypothesis and you'd accept the alternative. That mean difference at your school is not 2.5 hours. Well, I said small, but what is small enough? That really ties back to what we call our significance level. It's a value fixed at the beginning. The significance value level is something you compare your p-value against. It's going to be between 0 and 1, so 0 and 100%. And it can be thought of as the probability you reject the null hypothesis to accept the alternative when you shouldn't have done that. So when it was really better to keep that null hypothesis. If you don't state a significance level anywhere, we typically just assume it's 0.05. That's just traditionally what's accepted. We denote significance level by alpha here. Now, the more, depending on the consequences of making a mistake in our hypothesis test, rejecting or accepting when we shouldn't, you'd mess around with an alpha value and set it appropriately. I'll talk about that in a video about errors though. So what you really do is you compare, is this p-value less than your significance level alpha? If it's yes, reject your null hypothesis and accept the alternative. If no, just say you fail to reject the null hypothesis. This is different than accepting your null hypothesis. Most fields do this incorrectly. Most non-statistics people, when they fail to reject the null hypothesis, they accidentally will say, well, then the null hypothesis is true. That is not the case. It's just failing to reject. It's not evidence saying that your null hypothesis is true. So be careful about that. So for instance, if I'm looking at a scenario where A student government heading into student government elections. Mr. Melo is confident that Jen will be elected senior class president with more than 50% of the vote. In a simple random sample of 100 student voters, Mr. Melo found that 56 claimed they would vote for Jen. Is Mr. Melo's confidence reasonable? So you think he believes, or he wants to find evidence to support that Jen's going to get more than 50% of the vote. So my alternative hypothesis is Jen's going to get more than 50% of the vote. P is greater than 0.5. The proportion of voters who will vote for Jen is more than that. And my null is that P is just equal to 0.5. Well, assuming that that null hypothesis is true, I can calculate the probability I would have observed something as or more extreme than 56% of those 100 voters voting for Jen was 0.1375 or 13.75%. So if I have a larger significance level, say 0.2, I'd say my p-value is less than 0.2, so I reject the null hypothesis to accept the alternative. So I'd accept, yeah, I have strong evidence to suggest that Jen's going to get more than 50% of the vote. If I pick a smaller significance level, say 0.1, well, my p-value is not smaller than 0.1, it's bigger than 0.1. So I would just say I fail to reject the null hypothesis. And any other significance level smaller than that would also be failing to reject the null hypothesis. So you either reject it and accept the alternative, or you just fail to reject the null hypothesis. It's all about comparing this p-value to the significance level you want. So the significance level that you pick at the beginning is important. So I hope you found this introductory video helpful. I'll go over more examples in future videos. So if you found it helpful, hit the like button, subscribe, and have an awesome day.